Okay, so this evening's talk is by David Bowers from Bangor University. I've known Dave for a long time. He sent me he said he did send me a few lines just in case I didn't know him as well as I thought I did. So it says here he was born in post-war Liverpool, as I was, and he grew up by the sea in North Wales. And in his mid-20s, he decided to seek his fortune in the North Sea oil fields. And so he thought a good idea on the way to doing that was to train to be an oceanographer. So he did train to be an oceanographer, but he never made the second step of making his fortune. But he did instead find a great career researching into and searching about the physics of the ocean. And this has taken him to many places: Australia, Africa, North America, and on many cruises around the British Isles. David taught courses on oceanography for many years at Bangor University, from where you might know him from. And he retired in 2016. And since then, he's had time to travel for fun and uses any excuse he can find to write about his adventures. So this evening, he's going to talk about this Loch Ness Monastery and the work that the monks did, and this fascinating freshwater lake or Loch Ness. So over to you, Dave.
Thank you very much, Phil. Thanks for that wonderful introduction. And thanks to John as well for organising these history of oceanography seminars. Took a bit of getting going, but you did it in the end, so well done persevering. And I very much enjoyed the first seminar last month. It's always good to be reminded that science isn't entirely done. Well, the team isn't just scientists. You need all sorts of people to support you, people to drive the boat, as we heard last month, and people to make the instruments that we use, and people to publish the results that we get. So it's all a team effort, and it's humbling to be reminded of that. So thank you very much to the last speaker. This talk's a bit of a change of pace, really. Instead of traveling the world in the Challenger, we're staying in Britain, in Scotland, in fact, Loch Ness. 120 years ago, there was a team led by a Challenger alumnus, Sir John Murray, who was surveying the lochs of Scotland, the freshwater lakes, over 500 of them, a whole list they were doing. But they spent a lot of their time on Loch Ness, and they did more on Loch Ness than they did on the other lakes. In particular, they made detailed measurements of the temperature. And at first, they treated Loch Ness just like it was the Atlantic Ocean or the Pacific Ocean, and they were crossing it in the Challenger. They expected it to behave itself. And if they measured the temperature at a set depth on a set day, they expected that to be it. That would be the temperature at that depth. And they were quite surprised to find that that wasn't the case. They could make two measurements on the same day of the temperature at, say, 50 meters, and they wouldn't be the same. In fact, they could be quite different, 2 or 3 degrees different. And what they discovered was something which we would now call internal waves. So this lake, like the ocean, is stratified in the summer. It's got a layer of warm water sitting on top of cold water beneath, with an interface between them, a thermocline. And you can get waves on the thermocline, just like you can get waves on the surface. And what they were observing was that these waves traveling along the loch. And so the temperature at mid-depth would change as the wave went past. As the bottom layer rose up, it would get cold. And as the top layer came down, it would get warm again. They didn't have the terminology. They didn't call these things internal waves. This was a new discovery. So they had different words for it, but they knew what they'd found. They knew exactly what it was, and this was the first discovery, really, of internal waves anywhere in a large water body. It was very timely because oceanographers, real saltwater oceanographers, were just starting to think about the problem of internal waves. Yeah, mainly the sort of Scandinavian guys, Nansen and Helen Hansen, Ekman, were all beginning to think that internal waves might be important in the ocean, but nobody had ever observed any. They were observed first right here in this loch in Scotland. So this is the story of that discovery, but the scientists were helped in their work by the monks of Fort Augustus Abbey. So this picture on the left here, that's Loch Ness looking towards Inverness. So we're at the southwest end of the lake here. And at this southwest end, there is this old abbey. It's called Fort Augustus Abbey, and it was occupied by monks. Forget the order now. At the time of the survey was done in sort of 120 years ago, sort of 1903, I think they started, something like that. And the monks helped in a number of ways. First of all, they gave access to the loch. The abbey had gardens running right down to the water, so the scientists could get down there and launch their boats. And secondly, the monks loaned their boathouse. They had a lovely boathouse. And the scientists put equipment in the boathouse. They had recorders, recording temperature, amongst other things. And finally, when the scientists were away on other work, they'd gone off to survey another loch, the monks carried on doing the observations for them. And I think they enjoyed it. It was a bit of a change from their regular monk business. So it was good teamwork. Right, now I have to work out how to change the slide. Oh, there we go. So just a reminder, really, of what they discovered. We'd now call these things internal seiches. They didn't know either of those words in 1903. A seiche is a Swiss dialect word, and it's a sloshing of water. Bathtub slosh is a most familiar example of a seiche, where water rocks from one end of a water body to the other and back again. They were discovered in Swiss lakes by Farrell, and that's how they got their name. Farrell was brilliant at observing seiches. He worked out that the seiches could be complicated and be crossing the lake in different directions, and he worked out ways of unraveling all those things. But he only knew about surface seiches, oscillations of the surface of the lake. What's going on in Loch Ness is an internal seiche. It's a seiche on the interface between cold water at the bottom of the lake and warm water at the top. Does this little cursor show up? Can you see that, Phil? My little pointer thing there.
Yes, I can see it fine. Yeah.
Yeah, good. So in Loch Ness, the stratification is caused by temperature, by heat. So it's warm over cold. But you can create the same effect in a glass. This is a little experiment I did in a half-pint glass, really, in which you can put salt water in the bottom of the glass and fresh water in the top. And you can colour one of the layers with some milk or some food dye, something like that, so you can tell them apart. And then you tilt the glass over onto one side and put it straight again. And you'll create an internal seiche, an oscillation on the density interface between the salt and the fresh water. And it's a beautiful thing to watch. I'd certainly recommend trying it yourself. For a start, it's very slow. Any surface oscillations in a glass like this would have a period of a fraction of a second. On the interface, it's much slower than that. It sort of rocks quite gently from side to side. And the second thing is it goes on for a long time. Any surface oscillations would die down almost immediately. But these oscillations in the glass that I made lasted for about a minute before they stopped altogether. And what happens is that the interface rocks. So it starts off high at one end and there's no flow. And then the water starts to flow in the two layers, in that direction in the surface and the other direction in the bottom. So there's a sheared flow, and that makes the interface go level, and then it overshoots. So it's now high at this end and low at that end. And then the whole thing repeats. It's a regular oscillation of the density interface, or the picnic line. In a glass like this, the period of the oscillation, the time it takes to go backwards and forwards, will be measured in seconds. In a lake like Loch Ness, the period would be much longer. It would be measured in hours or even days for the oscillation to go from one end of the lake to the other. Now then, I've got some writing here, but I can't see it anymore because these pictures are over the top. I wonder if I can move that. Oh, yeah. There we go. So the time of the oscillation depends on a few things. It depends on the size of the vessel. That's why it's so much longer in a lake, just because the wave takes longer to travel the length of the vessel. It depends on the density difference between the layers. And the greater the density difference, the shorter the oscillation time. Yeah, you can work that out because in the case of the surface, for example, where there's a very great density difference between water and air, then it's quite a short period, sage, compared to the internal sage that we get inside the glass. And it also depends on the thickness of the layers. That's important. That has an effect in Loch Ness, and we'll see that in a moment. Right, so to the survey itself, it took a few years to complete the survey, 5 years altogether. They surveyed over 500 Scottish lakes, 550, something like that. And they did all sorts of things. They measured the bathymetry, the depth, biology, and biologists on the team who were interested in the animals and the plants and the lakes. And they did physics as well, so temperature and currents and other bits of physics. They tried really to reproduce what they'd done on the Challenger, but in Scottish lakes. Here's the great man himself, Sir John Murray, at the time of the survey, having his lunch. And here's his right-hand man called Fred Puller, or Sir Fred Puller. I have to move this picture again. So Fred Puller, FRSE, that's the Fellow of the Royal Society of Edinburgh. He was a much younger man and the driving force really behind the survey. And he also designed a lot of the equipment. They had boats that they used. On the small lakes, they would use boats of opportunity, like these rowing boats in the background, for example. People would loan them a boat. On Loch Ness, they had two permanent boats available to them. One was this beautiful steam launch called the Sunbeam. And another was a fishing boat called the Rhoda, and they kept the fishing boat moored at Fort Augustus by the monastery. But the steam launch they used as a travelling vessel, so they would go up and down the lake in that and make measurements. I think the Sunbeam is still alive. It's still there on the Thames today. It may not be the same one, but it seems to me that that looks about the right sort of vintage for a sort of an Edwardian steam launch. And it's certainly got the right name. So I think that's probably the boat they used. The scientific team, has some of them here. It did change. People joined it and left over the years, but this is sort of core members really. And I just draw your attention to a few names. James Murray has got the same name as Sir John Murray. They may be related. It certainly wasn't John's son. John did have children. John Murray did have children, but they would have been too young at the time of this survey. But James could have been a relation. James left the survey eventually to go and join Shackleton's Antarctic expedition in the Endurance. Somebody else to notice, I mentioned Puller. The genius of the party is this fella here, Watson. Watson's the guy who came up with the interpretation of their observations and realized that they were seeing internal waves. I think that was a step of great imagination. Wedderburn was a great communicator. He wrote many of the papers that came out of the work. And just make a note of these monks here. These two monks, although I think many monks helped, these two were mentioned specifically in dispatches, as it were. They were thanked for their efforts. And John Murray himself was in his 60s by the time of the survey, but this one wasn't a retirement project for him. He went on to conduct another survey of the North Atlantic. He did an oceanographic survey. So he carried on right to the end. And also about this time, he was busy setting up what eventually became the Oban, the Scottish Marine Biology Station. First of all, it was based in Edinburgh. That's where he set it up, and then it moved to Millport in the Clyde, and finally to Oban. Right, I think that's about it for the people. Loch Ness itself is in the Great Glen of Scotland. Some places to note are the south west end is Fort Augustus. That's where the monastery is and where most of the measurements were made. The northeast corner in Ness, that's the largest town locally, and halfway along, just here, there's a Urquhart Castle, a beauty spot, a place visited by tourists, and some important measurements were made there. I'll mention those in a bit. Here are the statistics, the dimensions of the lake, as recorded by the party, the scientific party. This is for their own measurements, but they had this list of 550 lakes that they surveyed, and they put them in order according to whatever they were talking about at the time. So if they were talking about length, for example, they'd have a list of lakes by length. And Loch Ness didn't make it to the top only made it to the top in one of these lists. It wasn't the longest, it wasn't the largest by area, it wasn't the deepest, but it was the lake with the greatest volume. It was number one in terms of volume. It's got a lot of water in Loch Ness. It's got more water than all the lakes in England and Wales combined. Right, what they did most was just measure depth, and they did that in all 550 lakes. The depths weren't really known at the time, so it was important basic work. This was the sounding machine puller, and if that makes you think of a bicycle, then you'd be right. It's made from bicycle parts. This is the weight, which would be lowered to the bed of the lake, and it had a little thing for sampling the mud at the bottom. As the wire was paid out, these were recording wheels, so these turned. Some turned faster than others, and they recorded how much wire had been paid out in feet, tens of feet, and hundreds of feet. They found that they bought sounding machines that were available commercially, but they found this worked the best. And you can see how they did it. They would clamp this to the side of the boat and then lower away. And it looks like it was a three-man job. There was a man to row the boat, a man to do the lowering, and somebody to sit in the stern and write down the numbers. And the results, I think, were really beautiful. The maps were produced by Bartholomew's of Edinburgh. And here's an example, Loch Garry. And they're unusual because they've got the heights, which were provided by the Ordnance Survey. So they're the brown things. And then they've got the depths of the lake and contours, which are all drawn. And these are all available on the internet. Every lake that they surveyed, you can have a look at and see what it was like. And I think they're, be a nice thing to have on your wall. The sounding machine, basic though it was, did find a use. It was loaned to Robert Peary, the American who went to the Arctic, explored the Arctic in 1905, and he took one of these sounding machines with him because he liked it. Now for temperature, they used various things. To start with, they didn't have anything fancy, but by the time they were doing their pioneering work on Loch Ness, they had reversing thermometers, and that's a reversing thermometer on the left of your screen there. I suspect that these were left over from the Challenger expedition. They certainly had reversing thermometers on the Challenger, and I don't see why they wouldn't have been used by John Murray on this survey. The idea is you clamp this sort of thermometer frame to a wire. There's the clamp there, V, and then there's a little thing to hold it vertical down there at C. And then you lower the thermometer to the depth you want, and you send down this weight, B, which goes down the wire. That's called a messenger. It hits that little lever, L, there, and that lifts up this bar, P, and that frees the thermometer on its axle there, this PP axle, and the thermometer's got a spring on it, so it turns upside down when the weight, B, hits the lever, L. It's called a reversing thermometer for that reason, because it turns upside down. And they had a very clever mechanism that as they turned upside down, the mercury in the bulb was separated from the mercury in the column, so that you recorded the temperature at that depth. You were left with a fixed length of mercury in the column. And when you brought the thermometer back to the surface, you could see what the temperature was at that depth. Um, they could do several depths at once. So you can see that when B hit this lever L and the thermometer turned upside down, it released another weight, B dashed, which would carry on down the wire and release the thermometer below that and so on. So you could measure the temperature at a number of depths at once. They were still using this technology when I came into oceanography. We used them to calibrate CTDs. And I well remember sending messengers down wires and reversing thermometers. You could feel the wire vibrate as the messenger hit the lever. They had different messengers. This was Wedderburn's favorite, nice simple spiral here, which did the job. And there's a profile of temperature in the lake in August. And even in August, you can see that the temperature fell to below 6 degrees at the bottom. Still very cold, even in summer. They also had a very early thermistor chain, which they moored off the fishing boat, the Rhoda, near the Abbey, St. Benedict's Monastery or Abbey. And it was connected by wires to the boathouse, where these recorders, where they recorded the temperature. Now, a thermistor chain is a series of thermometers, electrical thermometers. So they work by, these ones work by electrical resistance. So they have platinum wires whose resistance changes with temperature. So by passing a current through the wire, you can measure its resistance if you know the voltage of your battery, and therefore you can get the temperature. And they had 4 of those on a wire running down from the boat, and then the electrical signal was brought back to the boathouse, and they were able to record the temperature at 4 depths. It wasn't very successful. This was a very early use of thermistor chain, and they found it was temperamental. It kept breaking down. But when it did work, it enabled them to get measures of temperature throughout the day and the night. You know, even without being there, they could measure the temperature. The recorder is named after Callender. What was it? Hugh Longbourn Callender, who invented the platinum resistance thermometer. Now, I suspect he invented it because he wanted to put thermometers in places where it wasn't safe for humans to go, like the middle of Loch Ness, for example, but more likely, I think, in steam engines. I bet that's what he was thinking of. He was nominated for the Nobel Prize for the invention of the platinum resistance thermometer. Right, and this was the problem that they came across. Now, these are temperature measurements at the monastery. I can't see all the writing anymore because of these pictures, but these are a depth of 51 meters. So, you know, they were working in about 100 meters of water at that place. So this is sort of mid-depth. In October 1903, we've got temperature here plotted against time in days. So it's about 10 days worth of measurements. You see, they didn't make the measurements every day, but most days they've got a measurement, just occasional gaps. And what they found was that the temperature wasn't fixed. It varied by about 4 degrees or more. And it's interesting how you respond to that when you were doing a survey. I think a lot of people would have responded by saying, "Oh, that's a nuisance. I just want to know what the temperature is at 61 meters, and I don't want it to fluctuate like that. I'll take an average or something like that." But one of the team, E.R. Watson, saw his opportunity. He saw that this was something unusual, and like all brilliant minds, he spotted something unusual and realized it needed an explanation. And he came up with an explanation of it. First of all, he realized that those fluctuations couldn't be caused at a depth of 61 meters by heating and cooling of the lake. They're just too large. So there would be daily changes of temperature. It would get warmer in the day and cooler at night, especially at the surface. But you wouldn't get that sort of thing down there at 60 meters. And he reckoned that the only way those changes could be caused was by movements of water, currents in the lake, bringing alternatively cold and warm water. And he wrote up his results in 1904. I think. And we'll come to those shortly. He reckoned, this Watson reckoned, that the only way that well, not the only way, but the most likely way that those oscillations could be caused was by something he called a swinging of the interface. Well, we now call it an internal wave or an internal sation. He was familiar with, people did know at the time that you could make internal seiches in the laboratory. And the most common way was to put oil on top of water in a tank. So it's the same experiment that I described earlier in a half-pint glass with fresh and salt water. And then you sort of pick up one end of the tank and put it down again, and you get this swinging of the interface. So the oil on top of the water, and the interface goes down low at one end and high at the other, and then it oscillates. Water flows that way in the bottom, that way in the surface, and the interface rises at this end and goes down at that end, an internal seiche. In a laboratory tank, the period of such a seiche would be just a few seconds, but in a lake, it would be a lot longer. And Watson knew how to calculate the period of an internal seiche in Loch Ness. The theory was known, the theory was understood, and laboratory experiments had been performed. What hadn't been done before was observations in a large water body like Loch Ness. And he reckoned that for the temperature differences that he'd observed in Loch Ness, the period of the oscillation should be something like 3 days, something like that, the period of the oscillation in the lake. And in the lake, it is that sort of period, 7 days is a peak there, and then 10 days the next one. So the oscillation and temperature that they observed was consistent with this sort of rocking of the interface, as they called it. And the other thing he realized was that it must be a big oscillation, because they'd measured the gradient in temperature, the vertical gradient in temperature. It was about 0.1 degree per meter, something like that. So to get an oscillation of 4 degrees of temperature, it must mean that the interface is going up and down by about 40 meters. So that's a big wave in the middle, the mid-depth in the loch. And that would mean that a lot of water was moving from one end of the lake to the other as the interface went up and down by 40 meters. And he published his results in this geographical journal. Now, to me, I think that's a stroke of genius. I think he's taken a strange observation and he's come up with a plausible physical mechanism, which at a stroke explains a puzzling observation. So I think that's a brilliant thing, brilliant piece of science. Watson left soon after this. In 1904, he left the survey and he went to India. He became a teacher of chemistry in a university in India. And there's something slightly odd, I think, about his publication. He published his results in this geographical journal, but as a single author. Nearly everything else they did, this team, they did as a team. They published their results as a team. Watson didn't do that. He acknowledged the team, but he published the results on his own. He was a single author. I don't know why. It might have been that he was a bit reluctant to draw them into something which was controversial. It was a new idea, and maybe they didn't agree with him. I don't know. But there we go. He published on his own. Now, there was a lot of skepticism amongst lake people at the time, skepticism. They weren't so sure about what Watson was coming up with. They weren't sure that lakes would have these internal seiches as well as surface seiches. But gradually, people came around. And the first people to come around were oceanographers, especially the oceanographers from the Scandinavian countries I mentioned, Nansen and Helland Hansen and Ekman at the time, who were all beginning to say that these must be important things in the ocean too. But gradually, these things were observed in other lakes, and so people came to accept that lakes have internal seiches. And there was good supporting evidence in Loch Ness a few years after Watson had left. What they found was this is Wedderburn, one of the other members of the team. He took measurements at both ends of the loch simultaneously, so at Fort Augustus and also at a place called Doris, which is up in the northeast end of the loch. And I've plotted out his measurements here. So orange is the northeast end. There we go. This is temperature. And blue is the Fort Augustus end here, and we've got days along here, so it's about 4 days. And the thing is that when the temperature is low at Fort Augustus, it's high at Doris and vice versa. And that's consistent with an internal seiche because the interface would rise at one end when it was falling at the other. So that's good evidence that this was an internal seiche. Um, and It means also, or at least it implies, that the seiche is what we would call a single node. So the simplest form of seiche, just a sloshing high at one end and low at the other, rather than a more complicated motion. So this marked, I think, the sort of discovery, really, of internal waves in a large water body. And it was done on this lake first. Soon afterwards, they were observed in the ocean. Otto Pettersson is attributed with the first observations of internal waves, rather than surmising that they're there. And he did this in the stretch of water between Denmark and Sweden. And I never got that stretch of water sorted out, either Skagerrak or the Kattegat. And he did it by fashioning a float, which was heavy enough to sink through the surface waters, the light surface waters there, but too light to go into the deep waters below. So the float sat on the interface between the surface waters and the bottom. And he had a very long pole, bamboo stick, sticking up from this float. And he watched it from his boat. And over time, the pole went up and down as the internal waves traveled along the interface beneath him. So those are the first observations of internal waves in the ocean. And they were in 1909, whereas Watson and co. had done that 5 years before in Loch Ness. So it's a genuine first. Just a sort of footnote, really, to what happened later now. Our own Steve Thorpe, who many of you will know, came to Loch Ness in the 1960s, late 1960s, and he made measurements at Castle, which is in the sort of middle of the lake here. He had a thermistor chain, a much better one now than Watson's. He borrowed it from my old boss, Jack Derbyshire, and he acknowledges that in the paper. So nice to see that link. So he put his thermistor chain in Loch Ness in the middle. Now, of course, with a single node seiche, you wouldn't expect to be much of a fluctuation in temperature in the middle of the lake, because that's where the node is. It's sort of swinging around the node, and the node doesn't go up and down itself. So you wouldn't expect to see too much in the middle of the lake. But Steve did see quite a lot going on. And the reason he did is because the seiche had turned into something that was called a surge. Now, I mentioned earlier that the speed of the wave, the period of the oscillation, depends on the thickness of the layer. And you can see that the layer has a varying thickness. It's fatter at one end than it is at the other. So the period is different at the two ends of the lake. And that causes one end to catch up with the other. And it develops into a sort of traveling wave called a surge. It's the same exactly as the formation of a tidal bore in a river, but this is on an interface. So it's an internal bore. And just like an internal bore, you can get this sort of pattern developing. This is the sort of the front edge of the wave advancing off to the left there. And then behind you get these sort of little waves, whelps they would be called in a bore. So a series of waves, but on the interface now between the cold water and the warm water on the surface. And that's what Steve Thorpe observed with his thermistor chain. He saw these waves traveling past him, and they travel along the lake. They go sort of, they take 3 days or whatever it is to travel from one end of the lake to the other, bounce off the end, and then come back again. And he saw them coming back, and then they bounce again, and they go back. And they pass him 3 or 4 times before eventually the energy ran out. Now, there's an interesting footnote to this. Watson and co., the original lake survey party, had likely never heard of the Loch Ness monster. The story of the Loch Ness monster really became popular in the 1930s. That's when it sort of took off. So, and Watson was working in the 20 years before that. So it's possible he didn't know anything about the story of a monster in the lake, but certainly by Steve Thorpe's time, people knew about it, and they were starting to use echo sounders to look for monsters in the lake. And these waves, because they're a wave on an interface between dense water and less dense water, they reflect sound. So a boat with an echo sounder looking down here, looking for a monster, would see this sort of, wavy pattern traveling underneath it, going along at 10 miles an hour or something like that. So there was quite a fuss at the time when people sort of mistook these internal surges for possible Loch Ness monsters. Right. So one of the advantages of the history, looking into the history of something that's happened in an accessible place rather than in the middle of the Atlantic Ocean, is that you can go there. And if you, my wife and I did travel to Loch Ness to look at the place where this discovery of internal waves was made. And we travelled on something called the Caledonian Sleeper train from London to Inverness, or as my wife called it, the Caledonian Stay Awaker, because we didn't get a wink of sleep, I'm afraid. I don't think it was the problem of the train. It was just that we're getting a bit too old for bunk beds. If you fancy it, it leaves London every day in the evening, 9:15, travels up through Crewe, and gets to Inverness in time for breakfast. They serve you a nice little breakfast. And then from Inverness, it's maybe a sort of hour's bus ride to the Abbey at Fort Augustus. There are a few things there that the original survey party would have recognised. So this is a map of the Fort Augustus from the OS map, 1920. I might just add, by the way, that when the team were doing their survey, they didn't have much funding. They went ahead. People helped them with bits and pieces. People loaned them equipment, loaned them boats, but they didn't get any major government funding to do it. The Ordnance Survey were not really interested in helping, but they did give them their maps, so they could plot out the contours of the heights. So here's the monastery, Fort Augustus. It was certainly a monastery in 1920. You can see it looks like a fort. It was originally a fort. It's a big fortified thing, a Victorian fort. Don't know why they felt they needed a fort at the end of Loch Ness, but there it was. There's a lighthouse marked here. That would have been there when they were doing their survey, and this is the lighthouse today. I walked around this, and I don't see how it could possibly be a lighthouse myself. It's just solid walls all the way around. Don't know where the light got out, but maybe it was different in 1905 or 1920. There's a sort of walkway here, and that was there. That's a sort of breakwater that's marked on the map. And there's something else as well. The monastery itself is no longer a monastery. It closed in the 1970s. It's now sort of a holiday place, holiday complex, private. You can rent a flat there, but you can't go in it. The boathouse is still there. This is the boathouse where they kept their calendar recorders, and that's now a restaurant. So that's open to the public. I presume they kept their boats under here as well. We didn't expect. I went with my wife and we walked around here. It's a lovely place. You can understand that why the scientists, would have loved to turn up and work here. It's very beautiful. We didn't expect to find any sort of link to the science that was done there 120 years ago, but in fact there was a link, and it was a very nice surprise to find it. It's one of the joys of looking into the history of things when you just come across these things unexpectedly. And what it is the grave of Odo Blundell. So the monks of the abbey are all dead in their graveyard. They've got a graveyard there, and it's noticeable that it's very very level playing field. Whatever their grade of monk, the abbot or some lowly dishwasher, they've all got the same grave, same style of grave. Odo Blundell is one of the monks that's mentioned in the papers of Wedderburn and Watson for giving his help when they were doing the survey. And now his grave lies here, right at the end of Loch Ness, the lake whose secret he helped to discover. And that's it from me. Thank you very much, Phil.
Well, thank you, Dave. That's really, really nice talk. I got a couple of questions. One's from Gwyn. Just let me allow him to talk, and he can ask his own question. And if anybody else has got a question, just do the raise hand thing, and I'll allow you to talk.
Oh, thank you for opening the microphone. David, wonderful talk. Thank you. It really brought back to me some of the, well, minute amount of work I did alongside Steve Thorpe in a garden shed that he had on the north side of the Loch, just south of Castle. And looking for with an acoustic Doppler current profiler. So it's nice on these talks where they take one back to a little bit of one's own career. The slide where you had the cubic feet, I wonder if there was a millions missing there. Because it's such an astonishing number. Where are we? Yes, there is a millions missing. So it's 263,162 million cubic feet.
Thank you, Gwyn. Yeah, I'm sure you're right.
So, the National Library of Scotland has it at that. Anyway, so lovely talk. Thank you so much, Dave.
Okay.
Thanks, Gwyn. Good to know about that work in Loch Ness. So you were there.
I was with Alan Hall. If you remember, Alan Hall was Steve Thorpe's technical person, and so Steve had a mooring from the shed with an electric winch to a pulley on the floor of the Loch, some hundreds of meters out, with a buoyancy sphere on the top of that mooring. So he had it parked down when he wasn't there, but then he could release the brake and it would come up to the surface for him to attach his instruments to.
That's right. It's coming back to me now. He was sending sound upwards from the bed to the surface of the lake and measuring the depth that the bubbles came down from breaking waves.
Yes.
And there's now a law, Thorpe's law, which relates those things.
Also looking for convection from cooling winter nights. But thank you, brilliant.
That's good.
Okay, the next one is from Judith Wolf. Judy, do you want to ask your own question, or I can do it?
Hello. Yes, can you hear me now?
Yeah.
Thanks. I was just saying, how did they actually fund their work? Do they all have university positions or something?
Hey, Judy, nice to hear you.
Yes, hi, nice to see you.
They got bits and pieces of money, but I suspect, they were what we would call gentlemen scientists, largely. Yes. They were, they had their own private funds, so they didn't need paying. They did this for fun. And, the chap who went on to join the Antarctic expedition, I think they just saw this as a sort of way of living, really, an exciting life. Let's do something, and let's do something challenging, and and don't worry about paying us. We're amateurs. It was a time of amateurs, wasn't it? Amateur gentlemen.
Yes, thank you.
It's great from a point of view of pay rises. You wouldn't have to worry about all that sort of stuff.
One thing I remember is that there is actually a measurable surface sage in Loch Ness, but I can't remember what the period is. I think it's mentioned in Murray and Puller, but I don't know how they measured it.
You measured tides in the lake, haven't you? How big are the tides?
Well, M2 is only about 2 or 3 millimeters.
Millimeters.
But the sage, there is a surface sage, but I can't, which of course is set off when the wind blows. But I can't remember what the period is. It must be an hour or something like that, an hour or two. But that's mentioned in Murray and Puller.
Well, don't take any notice of my numbers, but I suppose you could you could work out the period
Yeah,
limitation on those.
yeah.
They're right.
Yeah. Okay, the next question is from Paul Butler. Go on, Paul.
Hi, Dave. Can you hear me?
Yes. Hello, Paul.
Hello.
Hello.
That
Nice to hear you.
That's all right. Nice to hear you as well. You have a very distinctive style of talking, which is, very, very easy to follow. And that was fascinating because, I didn't knew nothing about that. And it's very interesting to hear these stories about early scientists as well. I just thought I'd mention that we on our way to get to dredge Arctica from the North Sea. This is a clam that we work with. We went through Loch Ness on the Prince Maddock, and we were eagerly doing depth soundings, hoping to find something unusual down there. And all we found was a lot of depth, but no monster at all.
Yes, very good, Paul. I should mention that this is a navigable waterway, isn't it? You can go from one end to the other in a large ship, like
Yes, that's right.
Yeah, it's got locks, locks as in canal locks. It's not salty though. There's a low water flows to the North Sea down a river there, the River Ness. There's no salt getting into the other way.
One thing I did wonder, Dave, the idea of a thermocline, that's not entirely obvious. So, was that pretty well known at the time they did these experiments, or the time they found these internal waves?
Yeah, good question, Paul. I don't know. I think they were known about thermoclines. People would have taken temperature profiles in lakes and seas. They certainly knew about them on the Challenger expedition, for example, which was many years earlier. So, yeah, I think thermoclines were certainly known about by then. Yeah. They didn't really understand the physics of them very well, but
No,
they
that's what I was
existed.
wondering. But yeah, very interesting. Thanks, Dave.
Oh, nice to hear you, Paul. Are you well? Southwest of England,
thank you. Yeah, very well.
Good.
Right. Thanks, Dave. I think we run out of questions now, so thank you very much again. Our next speaker, I should say, is John Gould, who said he was going to listen to your talk from Australia, but I think he's failed to do that. It's probably something to do with the time zone. But anyway, he's talking next month on the 19th of March, and he's going to talk about swallow floats and Argo and 50 years of technology. So thank you very much indeed, Dave, and I'm very grateful to you for being our second speaker, and to everybody else for turning up. And this recording will be somewhere on YouTube, on the Challenger Society YouTube channel at some point, if you want to hear it again or you want to tell anybody else about it. So I'm going to stop the recording now.
Okay.
Okay.
Well, you can hear the clock.
Okay. Thanks, Dave.